Okay, so imagine a world where your data is truly, genuinely unhackable. I'm not talking just hard to crack, but impossible to crack, as in guaranteed by the fundamental laws of physics. It totally sounds like something out of science fiction, right? But it's a future we're actually building right now. So how are we doing it? How are we creating this unhackable internet? Let's dive in.
Right now, our entire digital world, I mean everything, is secured by digital locks. And these locks are basically just really, really hard math problems. So hard that even our best supercomputers would take like millions of years to solve them. But here's the problem. There's a new kind of lockpick on the horizon, quantum computers. And they're being designed for the specific purpose of solving these unsolvable problems. And they're going to do it in a flash. This isn't just a minor threat. It's a potential catastrophe for, well, everything we do online.
So to really appreciate the new solution, we first have to get our heads around just how fragile our current system is. Let's take a closer look at the code that's basically on the verge of being cracked wide open.
Every single time you use your credit card online, send a secure email, or check your bank balance, you are using something called classical cryptography. Systems with names like RSA are the invisible foundation of our entire digital society. They protect everything from our DMs to top secret government and military files. And the specific weapon, the master key that threatens to unlock all of this, it has a name: Shor's algorithm. You can think of it as the ultimate skeleton key for our current digital locks. It's basically a recipe for a quantum computer that takes the one thing that makes our encryption strong, the insane difficulty of factoring huge numbers, and turns it into a piece of cake. But this is where the story gets really, really cool. If a new kind of computer is the problem, it turns out a new kind of physics is the solution. We're about to see a massive jump from security that's based on math problems to security that's based on the fabric of reality itself. This quote really just nails it. Think about it. A hard math problem is only hard until someone or something is smart enough to solve it. But the laws of physics, they're not going anywhere. They aren't a puzzle you can just solve. They are the fundamental rules of how the universe works. And that represents a huge, huge shift in thinking. Instead of us trying to build a clever and more complex digital lock, we're just going to use a property of the universe as our lock. It's kind of like trying to break the law of gravity. You can't. It just is. And that is the unbreakable foundation of quantum security. So how is any of this even possible? Well, to figure that out, we have to open the very strange and, kind of spooky rulebook of quantum mechanics. These are the completely counterintuitive rules that run the world of the very, very small, and it just so happens they're perfect for building unhackable networks.
So this quantum toolkit relies on some seriously mind-bending concepts. You've got superposition, which says a particle can be in multiple states at the same time. You've got entanglement, where two particles become mysteriously linked no matter how far apart they are. But for our story, the most critical tool, the one that's basically our ultimate security guard, is something called the observer effect.
Okay, here's the absolute key to the whole thing. In the quantum world, you can't just be a quiet observer in the corner. The second you try to look at or measure a quantum particle, say a single particle of light, you change it, you disturb it, you literally leave a footprint. There's no such thing as a stealthy measurement. It's impossible. Let me put it another way. What if every single time a spy tried to listen in on your secret message, the message itself just instantly changed, tipping you off that someone was snooping? That's the powerful, practical security guarantee that you get from the observer effect. The spy literally cannot learn the secret without giving themselves away. So we have this amazing physical principle. How do we actually build it into a system for sending a secret message? We've got the theory down. Now let's see how it works in the real world. The technology that uses this principle is called quantum key distribution, or QKD for short. Now, the goal of QKD isn't actually to send the secret message itself. Its job is much cleverer. It's to create and share a perfectly secure, one-time use secret key. Once two people have that exact same key, they can just use normal encryption to talk because they know for a fact that no one else on the planet could possibly have a copy of their key. All right, let's walk through this using the most famous QKD recipe out there called BB84. So picture this. Step 1. Alice wants to send a secret key to Bob. She encodes the bits of the key, the ones and zeros, onto single particles of light, called photons, and shoots them over. Step 2. Bob, on the other end, receives these photons and measures them. Simple enough. But now here comes our spy in step 3. Let's call her Eve. She tries to intercept those photons to copy the key. But Remember the observer effect? That's step 4. The very act of her measuring them messes them up. She leaves fingerprints all over them, and this is how she gets caught. In step 5, Alice and Bob just get on a regular phone line, it doesn't have to be secure, and they compare a small sample of what Alice sent and what Bob got. They immediately see the errors that Eve created, and that brings us to the final step. They know someone was listening. They just toss that key in the trash, start over, and Eve is left with absolutely nothing. She's caught red-handed. And this is the most profound part. The real secret sauce of QKD isn't making the message hard to read. It's about making the act of spying itself physically impossible to hide. You can try to listen in, but you will get caught. Every single time. And look, this is not just some theory stuck in a lab. This technology is actively moving out into the real world, and it's laying the foundation for a truly unhackable future. Quantum encryption is already being put to work in some of the most sensitive fields you can possibly imagine. We are talking about securing communications between government agencies, protecting huge financial transactions in banking, and even building out national defense systems. Heck, there are even satellites in orbit right now, beaming quantum keys down from space, pointing the way towards a truly global, secure network. The ultimate goal here, the big dream, is a full-blown quantum internet, one that would offer theoretically unhackable communication across the entire globe. But let's be realistic, we're not quite there yet. There are still some pretty big challenges to figure out. For one, these quantum signals are super fragile. They get lost over long distances. The hardware is also incredibly expensive. And, of course, figuring out how to get these brand new quantum networks to talk to our old classical internet, well, that's a massive project all on its own. And all of this brings us to a really powerful final thought. For decades, we've been in this arms race, constantly trying to build stronger digital locks. Now, for the first time, we're building one that is fundamentally unbreakable. This doesn't just change how we protect our data. It could totally redefine what digital trust even means. So the question is no longer just how we'll protect our secrets, but what new kinds of business, what new ideas of identity, what new ways of interacting will we build, knowing they're finally sitting on a truly unhackable foundation.